Thank you very much for this opportunity today to talk to you about how we test on all levels our embedded secure devices. Who am I? So maybe some words to myself. I'm Stephan Puri-Jobi, Senior Lead Test Engineer in ID Tech Lab, which is an R&D department of HID Global. I work in Graz. This is where I'm located. I worked there for 4 years now and have 19 years of experience by now in software development and testing, especially of embedded devices. I'm in the happy position to lead a team of 15 people at 4 locations. And those 15 people are very diverse. Test specification, implementation, automation, CI/CD, everything in there. So we really try to give our best in testing our solutions at HID, which I will come to soon. What we are testing, in fact, are the future credential technologies of HID. Maybe some words to HID Global. We are headquartered in Austin, Texas, have over 4,000 employees worldwide and offices in 100 countries. Also in Austria, Graz, as I said, where I'm coming from. Part of Assa Abloy with 51,000 employees. HID Global has 6 different main areas where we work on, like secure assurance, physical access control systems, identity and access management, extended access technologies, citizen ID solutions, and identification technologies. All this together is somehow that we want to identify, that we want to authenticate, that we know who we are. This is something which is the core thing, what we want to provide in a secure way. And this especially for ID Tech Lab, so for this R&D part where I'm working for, where we use future credential technologies. And maybe for some of you, the big question now is credentials. What is this in the first place, a credential? So credentials are a technology to prove identity. Okay. Typically something which uses authentication mechanisms, cryptographics and so on. They contain keys and encrypted data. And typically we use a common set via APDUs, which is defined in the ISO 7816. So the common set contains of a select command, typically authentication, get data, and a put data. This is the basic thing which a credential should have. And a credential could be something like this card here, which you maybe know, which can open the hotel door for you, for example, or could act as an payment solution, could act as an identity card, could act as a driver's license. So many use cases you could have with this card, with this credential. But it could also look like this. A mobile phone can also have credentials on it. You know, if you want to pay with it, if you want to open doors with it, this is all possible nowadays. And this is also the interesting thing already here at for us at ID Tech Lab with the credentials we want to provide, because we want to provide one idea of a credential for all of those devices. And you can imagine that this already is quite challenging already as such, since we have different languages, like on a card like this, typically it's C on it. So I'm not sure if you can imagine that there is a small processor on it, a bit of RAM, some crypto coprocessor units, a bit of non-volatile memory, and it takes its power from the field, so an RFID card. On a mobile phone, typically, you have either Java or, depending on the operating system, Swift or Kotlin as programming language. So this is not really interoperable. You can really exchange this and reuse things. But still, especially for testing, we try to do this. And how do we know that this works? What we're implementing there? Yeah, spoiler alert, we do some testing. And testing on all different levels. And before I come to the test levels, I want to show you where we start from. This is the product requirement specification in our case. This is the document which describes the behavior of the device, of the credential which we want to implement. And this document consists of a lot of actual requirements where statements are in, and those statements are bound to requirement, and we then have to either develop this or test this. So for development team, it's quite interesting what we already saw in this early stage, so to say. If you give this requirements document to development team, they start developing. Typically, when something is missing or not fully clear, it's very easy to fall into this trap that you start to implement it the way you think it could be. Because you have your own ideas, what should happen if I have a select command and something is missing? No, I think I know how to select the things on this card. For us on the other side in testing, when we now have a look at this PRS, and the first test we do is even already before the first line of code is started, we do a static analysis, a static testing of this PRS, meaning simple review. We try to understand this PRS, try to understand all the requirements, how they interact with each other, already try to derive some test cases from this, and already there find issues which maybe come from under specification. Because a test case typically has a well-defined start, of course, and a well-defined assumption, what has to be happening at the end. And if we don't know what to assume after we execute a test, after we execute some commands to the card, then we have to immediately go back to the specification team and ask, hey, there's something missing. As said, we saw already that in development, and this is not, how to say, no finger pointing or anything, but in development, typically there is a lot of, or more ideas there, more creativity in how to implement it, because things should be done, of course. At the end of the day, you want to implement your function, you want to be done with it. And if something is missing, this is the easiest and the quickest thing to do. So testing on this level is already very important, we saw. And yeah, helps us a lot in identifying very early problems in the specification. Now coming to those levels, as I was saying already in the introduction, all of you know maybe this component level or also unit level, where we do unit testing. We take a function, completely isolated, have an own test driver, mock whatever is there underneath, and try to really isolate this function and try to test it. As said, for the many different versions we have here, we have different languages, we have different hardware platforms. The problem is this is all not really exchangeable. So we try to keep the amount of tests we have on this level rather low. Typically, everybody knows this testing pyramid where it says the foundation is the unit testing or component testing level. I don't really want to discuss this now. This is for sure true. The thing is just also in real life, you have to understand how can you be fast enough? How much testing is enough for your product to bring it out onto the market? This is something which we have to deal with every day. So we have project stress. We have to understand how to deal with this. And therefore for us, we try to reduce this amount of testing to minimum because as said, we cannot reuse it. The tests which are done for this card in C are hardly usable on this device because maybe the function is not even there at all. The same is for component integration level testing. So this is also done in from the development team in our case. Here we try to aggregate functions. We try to let the functions work with each other. We do not mock so much anymore. We have a test driver which tries to initialize first parts which are necessary to execute then a part of code. So for example, if you really have now a cryptographic algorithm that you really try to encrypt or decrypt something, and we call the function and see that the return of this function is if this is all correct. As said, again, we have the problem. This is all very hardware and language specific, so we cannot really reuse it. And all the time which is spent there has to be spent for every other implementation we do too. And so the good thing is finally we come to the system level testing now. And this is now the interesting part for us, because no matter if it's implemented like this or on a phone or on a tag or wherever, on your mobile, on your watch, there are many different ways. They all have one common interface, which is this APDU interface. This APDU interface is the interface on RFID where we already communicate with the card and have this common set available. This is where we now try to connect to with our test environment, which we created at ID Tech Lab to be able to do this testing. This test interface is, or this test bench which we have there is implementing actually all the requirements we have in the PRS. So we really do requirements-based testing here, try to have a full coverage of the requirements. And this means for us, we have to have, for example, positive and negative test cases. Positive test cases, we do what we should with this card, meaning we do a proper select of the card, we do a proper get data of some objects which are on the card, we receive this data, expect that we read the data which was previously put on the card. Already for these positive test cases, there are quite some different combinations what we can do. For this, we use boundary value analysis to understand what to take, which values to take to test a card, and equivalence class partitioning. I don't want to go much detail into this at the moment. Here, maybe just one thing we also saw already, especially for positive test cases. As I said before, we have to focus on test cases which give us value, meaning we would like to see something fail. We want to understand if the implementation was correct. So we have to have test cases which trigger something. Typically, the developers, when they commit the code to the code base or when they are developing, they already try their positive test cases, and they already typically try with all the default values which are there. So typically, what we saw, the developers, they take, if you have a range from 1 to 10, they take something 5, 6, 7, maybe 4. This is a safe range or a safe number to take. This should work. If it works, okay, fine, they commit it. So therefore, the important thing for us, for example, is take the value 1 and 10 boundaries. And another interesting thing is, speaking of negative test cases, negative test cases is very interesting for us as this card is not protected. So if it's out in the field, an attacker could try whatever he wants. And these are those negative test cases, meaning we try to use a command in a way as it is not intended. We try to use data which is not meant to be used. Too big, too small, for example. Everything outside of the spec is interesting here for the negative test cases. We want to see if the card in every situation gives back the correct error condition or error case. And also here we saw already that this is really interesting because this is something typically the developers on their side in the previous levels, like in the component level, don't do so much. Also maybe interesting thing we saw in our development, the ratio between the positive and negative test cases is slightly 1 to 4. So for every positive test case which we have for one requirement, we have 4 additional test cases which are negative test cases to see if the requirement really is also covered from this aspect, that nothing can go wrong, because we don't want to leak any information with a card like this. We don't want to give out any secrets. So we really have to do this negative testing too. Another interesting thing for us in system testing is how do we test this? Where do we test this? Meaning, do we really run on the card like this or on the phone, or can we use a simulator? Typically, simulators are much faster and give us a possibility of code coverage, meaning we understand where we are. It's like gray box testing, and we see what parts of the code are covered. We also can do then to the code parts which are not covered. We can do additional tests like static code analysis, reviews, again, things like this. But the problem is here always, although it's very convenient and much faster than the real hardware, it is not the real hardware. And again, here we see big difference between the different implementations of our credentials. If it's done for a mobile phone with all the technology we have for Android development on the Android IDE, this is really great what you can do there. Simulation is fast, it's quite accurate. You can work really nicely there also for the testing on a lower level, like on component testing. It's very different for a card like this, which is developed in C. You have to compile it first before you can test it. You have to download it to the either to the card or to an emulator. This all takes so much time. This is really annoying. So if you ever worked on a modern language, even like maybe if you tried this in Python or C# to do some unit testing and maybe even test-driven development, and you see how fast this is working, that while you are typing your implementation, that in the background the test is executed and showing you if you do the right thing or not. And then you go back to embedded development of a card like this. This is really very frustrating. So also there we try to take the frustration away from the developers and put this on system level as good as possible and try to test these cards on this level. Another interesting point for us, which also we can only test on the actual hardware then at the end, is performance measurements. So speaking of non-functional testing now. Performance measurements, there are two main things we want to test. One is the analog performance, meaning if you, as said, so it's not that critical with a mobile phone. A mobile phone has its battery inside. You have an active communication there typically, even with the NFC stack. So this is really something different. With the card, this is completely passive. You have to modulate the field with the card. So we have an analog performance which we want to measure and see if this is good enough, meaning how close do I have to go to the reader until the transaction can be finished. And the other interesting thing, of course, is the timing. How long do I have to put this card into the field close to the reader until the door opens or the police officer knows who I am, if I'm allowed to drive this vehicle or if I have paid, depending on the use case. Another important thing for us, memory consumption, of course. Again, I guess you can imagine that memory consumption on a mobile phone is not that important. On a device like this, it definitely is, as we speak here. We speak of kilobytes of RAM. So this is something we really have to take care of. So not only the RAM, also the non-volatile memory, creation and deletion of objects, for example, that we all do this in a clean way, that there is nothing going wrong, to understand if no memory is wasted on a device like this, as there's not much on it. Security features and attack countermeasures is also something we try to tackle with our test environment. And last but not least, anti-tearing. I'm not sure if many of you have heard of tearing. Also, again, this is something which typically only happens with a card like this. Why? This card is completely powered from the field. There is no battery inside, meaning as long as it's in the field, the CPU inside is executing, I'm able to write to the memory, for example, and everything is fine. As soon as I remove it from the field, we're done. And now the interesting question is, what happens if I have this in the field? I want to update my key maybe, because why ever? And during updating this key, I remove the card from the field. Suddenly there is no power anymore. I'm not able to finalize the write process. Something got written, not all. What is the state of this card then at the end? And also here we have test cases in place and methods in place to ensure that the implementation on this card always ensures either the new data to be there or still the old data to be there. Another interesting, also the last interesting test level for us is then, this is already after my team, so to say. So when we are done with all this testing and we think that this card, this implementation is correct, we hand it over to, or not hand it over, but put it together with other parts of our company, namely the parts who do the reader and parts who do the personalization. So typically we have your different business units and different teams working on different things. And of course, this is then the really interesting thing. For us, during our system testing, we personalize the card on our own. Personalization means we put some keys on, we put some data on, we know what is on it, we try to select the card, try to read it out, know what is happening. But this is not the normal case. Normal case would be that then, for example, out in the field, the hotel wants to issue a new credential like this one, and this is done by somebody else. So we provide the software on this card, somebody else provides the data, and already even somebody else then provides the reader on the door. And this all has to work together then at the end, of course. So this is also tested on this higher system integration level, where we also then test interoperability. If you have a look at our homepage, you can see we have quite a number of different cards, credentials, phones, and also reader devices. They all have to work together, of course, and this is something which is done on the system integration level testing. Endurance testing, how often can I put this card to the reader before it breaks? And general, the user experience. As we said before, how long do I have to wait until the door is allowing me to enter? Is there a special angle I have to access the card to the reader? Something like this. So this is then all done on a later case, on this later test level. So this was a quick overview on the different test levels we are doing. If you think this was interesting, what we are doing, and if you would like to understand more what the tests actually look like, anti-tiering tests. I did not go into details also on some of the other tests. There are some interesting details which I would like to tell you as soon as you are with HID. Thank you very much.